And someone made this video and edited the pitch of the sound to be how quickly the planet is rotating around its star. Because we're 500 and we're going to get an explosion coming up pretty soon. I think this is really nice actually. There we go. Like all of these planets are, I think, the Kepler mission, which is really, really good at finding planets. It has a telescope specifically designed to find them. I think this video ends prematurely because they stopped in 2022 already. There's only 5,000 planets, and now there's already this much more.
2 seconds.
Yeah, sorry. Okay,
just
perfect.
2 seconds. I'm just going to stop for a sec.
Okay.
So I wasn't screen sharing, that's my fault.
Oh, it's okay.
Oh, that's why. Did it on one or the other. Give me a sec, everybody.
Well done.
It's alright, it's people online told me.
Recording in progress.
Hello, everyone online.
Right, I'm just going to screen share. Wait me a sec. Okay. Right, so I think I'm going to ask you just to show that again for the benefit of people online, if that's okay, but I am going to have to mute on one device.
Can you show the first video?
Yeah, just not quite yet, not yet. Come on, you wretched thing.
There's these huge planets, there's these like really, really hot lava planets, which is crazy diversity. And we can start to have so many planets, we can do statistics on them. So say if you only looked at the planets in the solar system and you tried to say, how many planets are made of rock? That's like about half of them. But that's not really enough to say anything profound about what planets look like across the whole universe. And now we're starting to find enough planets that we can start to do these statistical calculations. If you just look at the size of planets, it looks here like there's a lot of planets that are really small, like Earth-sized planets. We're trying to estimate how frequently these planets are found around different stars. We think maybe between like about 10% of stars might have an Earth-sized planet. So that's actually quite a lot, considering there's billions and billions and billions of stars. Even though the first exoplanets we were seeing were more like Jupiter-sized planets, we call them hot Jupiters because they were really orbiting really close into their stars and really hot. But they're actually very rare. They're just easier to find, so that's why they were the first planets that we found. The other cool thing is there's all these planets in between the size of Earth and Neptune. We call these super Earths or sub-Neptunes. And there's nothing like this in the solar system. So we really have no idea what these things are, what they're made out of. Are they habitable? We really don't know. But that's why it's really interesting to look at them. So how do we measure how big an exoplanet is? You might have heard of this method called the transit method of detecting planets. It's actually a very simple principle, which is why it's nice to explain, is if a planet is crossing in front of its star, it's blocking out the light. So for measuring how bright the star is, we see a dip as the planet is crossing in front. It's actually a very simple principle, and it works very well. I mean, we're not going to get every exoplanet like this, because you can imagine, like, if we're looking at it, some planets might orbit like this, but there's so many planets that this is still really useful, and we're finding thousands and thousands of planets with this method. We can measure the size of the planet because you can imagine if this is a bigger planet, it's casting a bigger shadow, and this dip is a lot deeper. It's pretty obvious. The important thing here is the planet is not detected directly. We're not actually seeing any light coming from the planet here, we're just seeing the star. So we have to know the planet size relative to the star size. So we have to also be really good at measuring how big the star is. So let's see what that data really looks like. So I'm going to show, sorry, but this is this okay for hearing me? It's like a bit picking up like breathing, but it's okay. Okay, perfect. Okay, so we're going to look at some data collected by the Spitzer Space Telescope for a few days in October 2016. And each of these dots is how bright the star was when the telescope was looking at it continuously for all of these days. Okay, so how many planets do you see here? God. It's a really hard question. I also couldn't do this by eye. Anyone want to guess?
I'm not sure, but I see like 8 times with like white in between the dots.
Yeah.
Like planets.
Yeah. Oh, so yeah. So these gaps are actually when the telescope was sending its data back to Earth. Yeah. These what? Yeah. So this is. I should have given you this piece of information. That's a trick. This is the telescope can't be collecting data when it's sending the data back. So it's kind of taking a break here. The transits.
Is it just one?
Yeah, it's more than one.
Okay.
The transits are actually these.
Okay.
Do you all see this in the kind of light? So it looks different than that animation I just showed because it's been squished. But these dots are all different transits. How many? This is one star. How many planets?
Well, you have to look at
Yeah.
the frequencies
Yes.
between them and split it up and see.
Yeah, exactly. I think you need.
Can you just repeat that so other people online can hear?
So here you'd have to look at the frequency of each of these planets and kind of do some analysis to figure out how often the planet with the same shadow size is transiting. Anyway, the answer is there's 7 planets in here. And there's kind of a dot showing where each of these is passing in front of the star. So this is a famous star called TRAPPIST-1. It has 7 almost roughly Earth-sized planets that we name them B to H, and that's just the order that we detect them in. And it's usually also how close they are to the star. So B is orbiting faster, it has lots of different transits. We go all the way to H, we only saw it one time. We could still figure out that it was there. And you can see that the larger planets here are showing the biggest difference in how much starlight they block out. Yeah?
Does this mean some of these planets are orbiting the star multiple times over the course of a couple of weeks?
Yes, yeah, yes, good, yeah, they're really fast. So I'm about to show you this, yeah.
There are planets that orbit the star in like a whole lot of time. Can we detect those by other methods, or do we just have to wait until they're passing?
Claire, can you
Yes.
just repeat the question?
Okay, so the question is, if a planet is orbiting a star, say like on Earth's orbital period where it takes a whole year, are there other methods to detect these? The answer is yes, but it is a lot harder. And in this talk, I just wanted to focus on this because otherwise it'd be way too much to say, and this is kind of the easiest method to talk about. But yeah, there's other methods where you can detect something more like on Earth's orbit. I will also add to that now that everyone is so invested in finding especially Earth-sized exoplanets, we're building kind of smaller telescopes that are dedicated to do exactly this. So we have these really expensive, fancy telescopes in space, but there's also these small ones where they will, say, pick one star and actually stare at it for a really long time to try to pick this up. Okay, so here's this TRAPPIST-1 system. So I'll just show you how the data we saw kind of maps out onto what's going on in space. So here's all 7 planets orbiting. We can see each of them crosses. There's actually one here, you saw F and G pass at the same time. That's crazy that they figured out like how to separate that signal. But yeah, it's really cool stuff. We're getting really good at doing this. Okay, I think that's enough. So this is, as you pointed out, these planets are orbiting really, really quickly. This TRAPPIST-1 star is a really tiny star. It's a red dwarf star. So if to scale, all of these planets are way inside the orbit of Mercury. They actually it looks more like Jupiter and its Jovian, or the Galilean moons. This is about to scale. So the star is really not that much bigger than Jupiter, but it still has these 7 almost Earth-sized rocky planets. These planets are so close together that if you were standing on the surface, you would see them huge in the sky. Not that humans will ever get to this place. It's really, really far away, unless you're on this like intergenerational spaceship in the future or something. But that's what you would see if you were there. The other really cool thing about these red dwarf, really compact systems is the amount of sunlight they get is way more condensed. So because the star is so dim. So even though these planets are really close, they actually receive similar amounts of energy from their sun to like Venus, Earth, and Mars. So here we're just showing this is kind of the same scale. Earth is here, and so Venus is receiving about like 2 times Earth's sunlight. There's all these planets around the star TRAPPIST-1 that are receiving similar amounts of sunlight in between Earth and Venus. So that's really interesting to exoplanet scientists because it makes us think, what if these planets have similar temperature to Earth? What if they have oceans? We don't know yet if they do, but obviously we're really trying to figure that out. So that's the big question right now, is these planets could have similar surface temperatures to Earth. So why are these red dwarf stars such good targets for trying to find these Earth-sized planets with kind of Earth-like temperatures. So remember I was saying that to use this transit method, we also have to know how big the star is. Because these red dwarf stars are so small, an Earth-sized planet will cast a bigger shadow. So comparing Earth against the sun versus Earth against a smaller star, we get a much deeper signal. So it's a lot easier to see these. That's actually why most of the Earth-sized exoplanets we know about now are orbiting these kinds of red dwarf stars. We know about way less orbiting these more sun-like stars. That's great. Even if these planets are Earth-sized, getting similar energy from their sun to Earth, of course that doesn't mean they're anything like Earth. There's a few reasons why. A really important one is these planets are in a very different environment in space. By that, specifically, I mean that these red dwarf stars are really active. They are shooting off flares all the time. They have really harsh UV radiation, just a very different type of star than the sun. And actually, this much radiation can just blow the atmosphere away. If it's just like really close to the sun, imagine just getting like flared all the time. You probably don't want to live there. Another thing that's pretty interesting actually is, you know how when the moon is orbiting Earth, we only see one face, right? Because it's spinning at the same time that it's rotating around the whole planet. And that has to do with how close it is, how close the moon is orbiting Earth. And actually these planets have the same behavior because they're orbiting their star so close. They have one side of the planet is always day and the other side is always night. So that's going to have like a really bizarre climate. And we're trying to use like climate modeling tools that we use to study Earth's climate and apply that to these conditions to see what would happen and we get weird stuff. So we can't say that just because they get the right amount of sunlight, they are going to have the same climate as Earth. So we think that these atmospheres are easy to lose if they have any. However, planets can also make atmospheres. They're continuously making atmospheres because they have volcanoes that are just spewing out volcanic gas. How do we know they have volcanoes? Well, we don't directly observe them, but in theory, we expect volcanoes to be a really common thing on planets. We see them all over the solar system. Recently, we found evidence of a volcano on Venus. Of course, Io, a moon on Jupiter is crazy volcanoes, and that's just because melting stuff inside the planet and bringing it up is a way to cool down. And if the planet is kind of generating heat with all its mantle of convection and its radioactive elements, it has to get rid of that. And it does that by melting and putting the gas comes out of the volcanoes. So this is going to happen, we think, on a lot of planets. It's easy for planets to just make new atmospheres at the same time that they're losing atmospheres. So we don't know for sure if a planet doesn't have an atmosphere. We have to try to find them. So that's the question, right? Like, are these planets, even though they're Earth-sized, they're orbiting red dwarfs, are they similar to Earth at all? The first question is, do they have atmospheres at all? This is the kind of level of inquiry that we can do, right? Because as we know, these things are so far away, they're so hard to measure. It's really hard to say, like how much CO2 is in the atmosphere of this planet. First, we have to ask, do they have atmospheres? And that's what we're doing right now. I would argue this is the most important and biggest, hottest question in exoplanet science. So people are, trying to be getting the Nobel Prize and stuff. So they're like racing to look at all these planets and try to find atmospheres. So far, there's no conclusive evidence of an atmosphere on a rocky planet. Recently, there's a tentative detection of one on this planet called 55 Cancri E, which is in the 55 Cancri constellation. I honestly don't know what constellations are, but I would argue this planet is not really a rocky planet, but this is a different kind of story. Anyways, there is only one way to be sure that we are finding an atmosphere on the planet. We can't just look for gases, because actually they might be coming from the star. If we're using a telescope on Earth's surface, they might be coming from Earth's atmosphere. It's actually kind of hard to disentangle this, but there's one really, really good way to look for an atmosphere, which I'll explain. And it comes down to the effect that atmospheres have on the climate of a planet. And what is that? They recirculate heat, right? So like this happens on Earth. The equators get a lot more heat than the poles. And if you didn't have an atmosphere, the equators would be way, way hotter. But because the atmosphere is circulating heat from the hot part in the equator to the cold part, you're kind of balancing everything out. So we can use the same principle to look at these planets that have the permanent hot day and the permanent hot night hemisphere. If this planet had no atmosphere, right, its day side would be so hot, it might even be like molten lava. It could be really, really hot. And the night side would be like, I don't know, like so cold, like almost absolute zero, I think. Maybe not quite, but really, really cool. Right, okay. And that's just because this day side is permanently facing the star, so the night never gets heated at all. Okay, if we had an atmosphere, this allows the gases in the atmosphere to move around the planet and warm up the night side. So that means the day side is cooler than it was, and the night side is warmer than it would be compared to if there were no atmosphere at all. That all makes sense, right? Okay. So if we observe the planet for its whole orbit, which you can do for these planets because they only take a few days to orbit their star, we can measure the difference between how bright it is on the day side and the night side. And so I already told you about this effect of the planets passing in front of the star and blocking out light, right? That's what we're calling the night side. That's what we're calling the transit. Here, we're kind of seeing the night side because that's the thing we're comparing. If we compare here to here, the thing that is different is how much brightness is coming from the night side of the planet. And meanwhile, as the planet passes behind the star, as it's called the eclipse, we are seeing the light from the day side, so we can say how bright the day side of the planet is. And then by comparing what temperature we infer from how bright this is, we can say how much of a difference there is. So if there's a really big difference, then there's probably no atmosphere. If there's a smaller difference, then there could be an atmosphere. And this is a great method because there isn't really another way that you could even out the temperature differences. Like people have looked at like lava currents trying to like transport lava like flowing from the day to the night, like it's not efficient and not that distributing the temperature. Yes?
What about planets that are not tidally locked?
Yeah.
Can you repeat, please?
So what about planets that are not tidally locked? You're right, this doesn't work. But we have so many planets that are tidally locked, and this is most of the planets we're looking at, that this is the method we're going to use. Yes. Okay, sorry.
Are you measuring the brightness of the planet directly?
Yeah.
Can you just say again?
Are you measuring the brightness of the planet directly? Only by seeing how much difference there is between the star and the planet.
You've got a curve,
Yes.
a continuous curve of
But sorry.
You've got a continuous curve all the way across.
Yeah. So this curve is just the light from the star, but it's actually like the star plus the planet. So this is the star plus the planet because we see some light. Yeah. So I should clarify. Here we're looking at the infrared brightness, which is related to how hot the thing is, right? And yeah, this only works for planets that are hot enough to be emitting this infrared emission that we can detect, but it's too faint compared to the star, so we can't resolve it, right? Like this whole thing is 1 pixel, so we can't actually see like where the light is coming from.
So
Yeah.
your text is actually not correct then. You're observing the planet and the star at the same time.
Yes,
Right.
yeah, so observing the planet and the star, yeah. Yes,
So the mean level of the gentle curve of the brightness of the star,
yeah,
fluctuations from that to that to the planet.
yeah. Anyway, yes.
So, is it possible that you could have a star that is cold, which is very reflective based on the surface?
Again, can you repeat?
Can you repeat? I don't.
So,
Hang on.
Sorry.
So if I understand, we're sort of inferring the temperature based on the brightness, and that's to do with like how much is reflected off the day side of the planet.
No, it's emitted in infrared light. So it's like a T to the 4 thing, right? Yeah. Yeah, you could do this for reflected light too, but it turns out that there's so little reflected that you couldn't do it. So this method works way better. So it's infrared emission from the planet. Yeah. Does that make sense? Any more questions, or I'll continue? Yeah. Okay, so this, we're trying to do this with the James Webb Space Telescope, also I'm guessing most of you have heard of, is the most powerful telescope in the solar system. I won't say in the universe in case there's aliens that have better telescopes. But this is a really expensive and really valuable instrument. And the people in charge of it are trying to use 500 hours of using this telescope to look for atmospheres around rocky planets. That's a lot of hours. It's really, really hard to get time on this telescope. I've been part of teams that have applied and have never been successful. It's extremely competitive. I think it's like 1 in 100 proposals gets through or something. Just because it's so powerful, everyone wants to use it. And they're using 500 hours to look for atmospheres around rocky planets. What they want to do is figure out which planets have atmospheres by observing a lot of them. Here, these are all real planets that they plan to look at, so there's like dozens here, and try to figure out what separates planets with atmospheres from planets without atmospheres. And this has been called a cosmic shoreline, which is a really catchy phrase, and that's, I think, part of why people are really invested in seeing if it's real. So if these planets are getting more radiation, it means they're less likely to have atmospheres. So if the planets have stronger gravity on the surface, it's easier for them to hold on to their atmospheres. So it's been theorized that there's this cosmic shoreline separating the planets with atmospheres. So Earth and Venus are here. Mars is kind of right on the edge versus planets with no atmospheres. So like Mercury, for example, is right here. But we're not really sure where this is. This is like a theoretical idea. We're trying to test this by looking at a lot of planets. And to do this, we need, of course, we can't just look at 1 or 2 planets. We have to look at dozens to see if what we're seeing is real. So Because actually doing this takes a long time, and even with 500 hours, it'd be hard to look at dozens of planets. So the idea that this team had is they want to take a shortcut. Instead of looking at the planet on its whole orbit, they're only going to look at it right, oh no, I missed it, right there. And so when the planet is behind the star in its eclipse. So here, you only see how bright or how hot the day side of the planet is, but you don't get the rest of the orbit to have that to compare it to. So that could work if you know for this particular planet how bright it should be if it had an atmosphere and how bright it should be if it were a bare rock. How bright is the bare rock?
How do you know it is a bare rock?
Yeah. Well, this is what they're trying to ask. It would either be a bare rock or it would have an atmosphere. I don't think. It doesn't have to be a rock. Well, it probably is a rock. It's these things are so hot that they're probably not ice, which helps. But yeah.
Hang on.
Yes.
Probably a very stupid question, but what if like a planet was liquid rock, so basically lava?
Yeah.
In that case, wouldn't it emit some sort of light of its own and therefore not be bare rock?
Yeah. Well, do you mean emit light, like?
Like lava normally makes light, doesn't it?
Yeah. Well, everything is emitting infrared light, so that's why you are seeing infrared from anything. So if there's so like if it's just hot enough to be lava, or just below the temperature that rock is melting at, you'd still see some infrared radiation.
Yes, true. Sorry, I forgot that.
Yeah.
That correlates.
Yeah. Yeah, but that's a great question. Some of these planets definitely could be covered in lava, so you'd have to know how bright is the lava. But this is actually a bit of a problem, because I think that we don't know this. For like an exoplanet so far away, we don't really know it's made out of the same stuff that we see in the solar system. And even if we look at the rocky planets and moons in the solar system, they're made out of a lot of different kinds of stuff. So if you want to compare just how bright the day side of the planet is to what it would be, or how bright it would be if it had an atmosphere, it gets a little bit tricky, right? So here's like two very common rocks on Earth. So basalt is what we see on Earth's ocean floor. I think it's like fairly dark. It's not that reflective. Granite is what Earth's continents are made out of. That's like basalt. If you melt it again and cool it, and you have some water in the crust, you can make granite. Granite is really light. It actually reflects a lot of light. And if you had a planet covered in granite, I don't think you would, but this is just an example. It would look a lot brighter than it would if it were covered in basalt. And actually, the moon is covered in this stuff, which is anorthosite, and this is like a really, really bright mineral. It's almost pure white. If you had an exoplanet that was completely covered in this mineral, it would look brighter than if it had an atmosphere.
Not in infrared.
Yeah, so if it's highly reflective, it's reflecting the light, so it cools down. Yeah, so it's like Antarctica reflecting lots of sunlight. So this is a team in Oxford that I was a part of, where we tried to look at all kinds of different rocks that might be possible without knowing actually what's the most likely, because we don't. And we looked at whether or not they would be disguised as an atmosphere, and turns out that lots of them would be. So when we published this the Americans really didn't like it because we basically said your like 500 hours of telescope time is not as good as you thought it would be. And we're still kind of talking about this, so we'll see what's going to happen. But the moral of the story, I think, is planets are actually just really big, complicated rocks. And you have to know how rocks work, and you have to understand the geology of Earth and other planets if you want to really figure out what these exoplanets are. And this is something that we're doing here in Oxford, and it's really exciting stuff. And I think it requires bringing a lot of different people together, so from earth sciences and astronomy and even like microbiology if you're looking at, you know, signs of life on these planets.
Are there any tests that will tell you whether you're right or not?
Yeah.
Can you repeat?
Are there any tests that could say if we're right or not? Yeah, so that more intense method where you do like the whole orbit of the planet, I think you would have to follow up and do that if you saw an atmosphere, or if you saw something that looked like an atmosphere just with a smaller measurement, and then you could confirm using that. Yeah, so something else I just wanted to end on is I don't think that not finding an atmosphere means that like we failed as scientists. I think that's also really, really interesting. And part of it is as we're looking at these bare rocks with this telescope, we are actually doing that. We're seeing a signal that's coming from the crust of another planet directly. And that's carrying information about what that planet could be made out of. So we're starting to do this, and this maybe answers your question a bit too. So here's this planet LHS 3844b. We've definitely ruled out an atmosphere on this planet. So we know that if we get the spectrum of light from the planet, it's actually the rock. And we can start to use that to figure out, by comparing that spectrum to spectrum measured in labs, what that planet is made out of. So if we can do that, then we get a sense of, not maybe for your planet you care about, but in general you can get something about the diversity of the types of rocks you get on different planets. And I'll leave it there, but I'd like to take any more questions also for the people online. And yeah, thanks so much.
I'm going to stop you there. If we could just give her a round of applause. Thank you very much, Claire. We actually take a break. We will take a break, I think, because we've been going quite a bit of time with all those questions in the room, brilliant as they were. Quick break, just a few minutes. Snacks, drinks in the room here. Those at home, take a rest, and we'll come back and have questions. For those online, do start putting it into the chat. I'll apologise again for my cock-up with the sound earlier. I got so distracted at the beginning of the cafe, which is entirely my fault, so I totally forgot to share the screen and get the audio sorted. But you really didn't miss very much, and I think I might tack the little video onto the end of this recording so that everyone can see and hear it properly as it's meant to be done. But you didn't miss much of Claire's talk at all. Thank you very much, guys. See you in a few minutes.
Very well done. Jane.
Okay, everybody. Thank you very much. So I should have explained at the beginning, I've done everything wrong today. Should have explained the format of the cafe is a short talk followed by a quick break, and then after that, discussion. So the way that we do this, partly to make sure everybody, whatever their hearing abilities, can hear everything, is I will come to people in the room who've got something to say and get you to use the microphone. Some people find this easier than others. Don't do that. It doesn't work. Okay? You have to have it pointing at your mouth. Lady Gaga job, la la. Okay? That's the way to do it. So don't pull it over there. It doesn't work either. Please remember that some people need the amplified sound to be able to hear properly. Is your microphone back on?
It's about to be, yes.
Lovely, perfect, excellent. We have people online as well. We've had a very lively discussion already today, which is great. So I'm first going to come to anybody in the room who wants to stick your hand up if you want me to come over to you. Thank you.
Try and get this right, is that right?
Yeah.
Question about, if you like, selectivity of these things, because you focused on the red dwarfs, the planets really close in.
Mm-hmm.
And first off, I mean, how many of the solar systems we know of, is there a bias towards wanting the plane of the Milky Way? Are all planetary systems more or less in the same plane? What kind of angular tilt does there have to be away you can't see them at all?
Right. So the geometry of the orbit has nothing to do with the Milky Way. So like that, it can be completely random. So like the Milky Way is in one plane. Actually, most of the stars and planets are in that, because the other stars are like a weird type of star that don't really have any iron, and they just make less planets. So so like most of the planets in the Milky Way, but the geometry of the orbit relative to us is completely random. So yeah, there's a very small fraction of planets that we can find this way, but like I was saying, there's just so many planets that we still have enough to work with.
Yeah, so the ones you're choosing to look at is a very small subset, chosen by what you can actually see of all the different planetary types that are out there. So it's quite a question of, you know, you've got a nail and you've got a hammer, then you know that works, but there are many other things that aren't in that class.
Yeah.
I mean, no, not saying it's a bad thing, but have you any idea of what fraction of what there is out there you're actually seeing?
So I think for what the fraction of planets that we have detected, I think for like giant Jupiter-sized planets, it's something like 80% that are close to us, just because they're easier to find.
That you're detecting them by wobbles.
Exactly, by wobbles, by the radial velocity method. So we combine different methods of detecting planets. I only mentioned one just for time. For the small planets, it also depends on how far away they are. It can, for Earth-like, Earth orbit planets, it could only be like a few percent. But it's really hard to answer that question, right? Because how do you know how many you don't see?
You don't see.
Yeah.
Okay, I'll pass on. There must be other people. Correct.
You can always come back. I have one question, which is, I'm probably being stupid or missed something, but how do you sort out the business of how far the planet is from its sun and its size? Because obviously the shadow it casts will depend on how far away it is. So how do you sort those two values out?
The size, like I said, is the dip. How far away it is has to do with one of Kepler's laws. So we see how long the year is, and then Kepler said that the orbital period is like a function of how far it is, and that's just like celestial mechanics. So we've known that for centuries, so that's how, but yeah. Apparently, not.
Kepler's still right,
yes.
Wow.
I've got two questions. Just firstly on the Kepler's law.
Yeah.
Could that vary if it was like an eccentric orbit that was in an ellipse shape? Yeah.
And so that comes into this. I think for the relationship between the orbital period and how far away it is, the eccentricity doesn't matter. So I don't think it's in the equation, but it is for other things. So actually the eccentricity is really important for like, the climate of the planet, and it's not that well constrained. So yeah.
Could I ask one other question?
Yeah.
Claire, can you just move one step to the left? Perfect, because at the moment you're unfortunately you're on one of those bits of wiring under the floor, which interferes. Yeah.
Okay.
I had one other question. Right at the start of the talk, it was mentioned how, like, not that long ago, exoplanet research was much more niche, but because loads more planets have been detected, it's like a blossoming field.
Mm-hmm.
What have been the main changes that have allowed all these planets to be detected?
Technology.
Is it like any particular telescope or something?
So the Kepler Space Telescope was the first telescope in space that was only designed to find exoplanets. So it could use its whole mission, and like every hour it's looking at stuff to only find planets. So even like James Webb was actually designed to look at like really distant galaxies. So only like 20% or something of this telescope's time is being used to look at exoplanets. So it's just, having more telescopes that are dedicated to doing this. I think that's the main thing.
Just one last question.
Yeah.
I get this is quite a difficult question, but do you think it's likely there'll be like technological breakthroughs in the near future that will really change exoplanet research?
Yeah, yeah. This is kind of outside of what I do. I've seen, like, one of the limitations is like how big the telescope can be, right? Because if you want to launch into space, you can't launch this like mirror is gonna shatter. I saw a talk recently where someone was saying they could like make a telescope mirror out of this like liquid. So you launch this like ring, and then you can, I don't know, make this almost like planet-sized thing. There's basically like no limit to how big it is. I think this is like, if that ever works, it would be like so many decades away. But yeah.
That'd help you discover a lot more planets.
Yeah, you could just get a lot more light from the star, so you could be more sensitive to like very tiny changes in the brightness.
That sounds interesting.
I don't know if that will ever happen. Yeah, but there's people that do this.
Basically, a question to a question.
Yes.
You said that stars outside of this plane normally have less iron or produce less iron. Why?
I have no idea.
So we just happen to be on the plane with all of the iron stars.
Oh, that's like most of the stars.
And the others are outside, and the ones outside happen to not be iron stars.
Yeah, I think it's also related to really, really old stars are just born when there's less stuff around. Like the stars from the earliest universe. Like you make iron and all these heavy elements when there's like different supernovas and different generations of stars. So the older the universe gets, the more diverse the chemistry is. So I think the stars that are being born now will have the planets with the richest chemistry.
That's very interesting. I'm just going to go online for a couple of messages. Give me a sec. Okay, very early question was, are the orbits elliptical or circular, please?
Yeah, so I think this is already asked. We don't, it's kind of hard to know this, but if you stare at planets for long enough, you can kind of work out, it's not just these, there's actually 6 parameters that you need to describe an orbit completely. And you can get better constraints on them the longer you stare and the more data you have. So it varies a lot. I think there's some planets where we think the eccentricity is like 0.8, so that would almost be like this. There's some crazy ones. A lot of them are circular, a lot of them are eccentric. Yeah, they're weird.
Okay, and then next one is, in addition to the basic knowledge you're gaining about these planets, are there any spin-offs, a bit similar to the Moon programme, where there were spin-offs for daily life and things, advancing technology, things were developed in order to do the science of going to the Moon?
I'm not really sure.
So is there anything out of this kind of research that might affect areas outside astronomical research?
That's such a hard question.
I mean, for instance, would looking at other exoplanets tell us something more about the Earth that we ought to be finding out?
Yeah, well, I think there's the kind of philosophical answer of understanding how Earth fits in. Like, is Earth a rare outcome of planets or not? And that's actually something that we don't know. I'm not really sure if that's answering the question. I think for me, that's like one of the most interesting things, is figuring out, is Earth weird or is Earth easy to make? We don't know that. We also can, because we have so many planets, we can also start to see like how they evolve in time. Because like all the planets in the solar system have the same age, right? We know planets that are like 500 million years old, like 6 billion years old, so we start to see this kind of trajectory. So we're not quite there yet, but you know, once we have like 10,000 planets or more, you can start to kind of almost do this like matched kind of studies and stuff. So yeah. You
can find planetary twins.
Yeah.
Is the day side measurement just before eclipse or just after, or both?
So it's both, yeah. So you're making the comparison of just before and during. So that's how you see the difference.
Okay. And he's also asking, how do you know where the planet is in its orbit if you're only measuring the truth? a short segment of it.
But if you see if you can tell the period of by looking at multiple, if you see more than one transit, you know the period. And as I was saying, you can just use Kepler's law to figure out like the period and the distance. You don't know the whole geometry of the orbit, but yeah, does that answer the question?
And I presume you can figure out where the transit is because that's where the changes are happening.
Yeah.
So focusing on that.
Yeah,
and
exactly.
Keep going back to that. Right. Okay. And he's asking, I think this is quite early, well, no, a little bit of time ago. Could you recap how you infer the presence or absence of an atmosphere from one measurement?
Yeah, so you don't really have to make a lot of assumptions, and I think that was one of the points I was trying to make.
Go on then, assume for us. Tell us what the assumptions are.
So if you assume that all bare rocks are really dark and not reflecting light, and you know that all atmospheres are reflecting light and have a high albedo, then if you infer a high albedo, then you can say that's an atmosphere. But in order to do that, you have to understand the range of albedos you get without an atmosphere.
And in that situation, in that kind of range of inference, is the moon, which you referred to as being particularly bright, is that an outlier or is it within that range?
We have no idea what the range, we have no idea. We can kind of do some theory to say like what, if we kind of model the compositions of crust you get if you like put in different ingredients. But the moon is also, it is weird. Like the crust on the moon formed in some weird way. It's not the same way that the crust on Mars formed, for example. But the idea is, a priori, we don't know that. Yeah.
I think this is raising more and more questions. Interesting. I'm going to ask one myself, which is a bit linked to that. So one of the points you're making was about rock, whether it's solid, whether it's liquid, and all that kind of thing. So you said that these red dwarfs are much smaller, the planet's much closer. Is there any idea what the gravity would be like on them?
Yeah,
because obviously the sun is a completely different sun, so...
You mean the gravity on the planet?
Yeah, the gravity on the planet, so that might give us some idea about what...
Yeah, that's pretty straightforward, actually, because for this measurement of the transit, you know the radius, right? And then if you use this wobble method, you can know the mass, because they're sensitive to different things.
Okay.
So if you can detect the same planet with these different methods that are sensitive to both the radius and the mass, then you can calculate the gravity. Yeah.
Okay. So, and the wobble method you haven't talked about today, but that's another one.
That's another one, and that will only tell you the mass. It won't tell you the radius.
Yeah.
I'm a bit slow, I'm sorry. Could you show the video of the planet going around the sun?
Sorry.
I haven't quite got this.
Yeah. Is it this one?
So the brightness goes up when when the reflection from the planet is added to the light.
Yeah.
That's what you're saying. And then why is the second one deeper than the first one?
So this one, right, you can't see. Yeah, but this one's deeper because you have this whole planet casting a shadow. So like a lot of the light is blocked out. This one is actually just what we're not seeing from the planet. So here we see the planet plus the star. Here we only see the star. So planet plus star, and then this is actually the planet's emission in infrared.
Oh, yes.
So see both places together.
Mine.
Yeah.
Right. I'll have to...
Thanks, me again. Looking at your last slide, you don't necessarily have to show it, but you say you could pick up IR signals, spectroscopy signals from the rocky planets and have a go at what kind of rock it might be.
Yes.
Obvious follow-on from that is if the planet's got an atmosphere, presumably you can pick up IR signals from that. The obvious ones to go for would be water, oxygen, CO2.
Definitely, yeah.
Have those been found?
So not on rocky planets. On say like Jupiter-sized or even smaller planets like these sub-Neptunes that are maybe like twice as big as Earth. We found lots of evidence of water in the atmosphere, methane in the atmosphere, CO2 in the atmosphere. It's the same technique.
So you've only so far with rocky planets found relatively bare ones with no atmosphere.
Yes.
Okay.
Yeah.
Good. Okay, let me go back online. So why is moon rocks so different from Earth rocks? You kind of hinted there isn't an answer to that, or not one you're aware of.
It's kind of a complicated explanation, but like the moon formed in a giant impact where some kind of big asteroid thing hit Earth and then like ejected a bunch of stuff from Earth, and that kind of like recooled and made the moon. So like in that stage of taking like a weird part of Earth and then recooling it, you ended up making this particular kind of mineral on the surface.
And that's something that happens quite a lot. You were referring to it before. When you heat rock up and then cool it again, it changes its structure, doesn't it? Very often. Different crystal structures.
Yeah.
Okay. So do all measurements include spectral analysis? It sounds like they do, because there's no other measurement you can take, is there?
Yeah, well, some of them are just all the wavelengths at once. And we do that because the thing is, like, we only get a number of photons per wavelength. So if we want to have as many photons as possible, we kind of have to count them all together. If you have a lot of photons, then you can start to do this, where you can put them into the groups. So yeah, like lots of instruments are capable of the spectroscopic measurements, but sometimes it's just too noisy, and you just have to look at everything together.
Doesn't that make it harder to pick up atmospheric constituents?
So the question was, doesn't that make it harder to pick up atmospheric constituents?
Yeah, exactly. You can only find atmospheric gases with spectroscopy. If you're looking at trying to use what's the CO2 content of this atmosphere. So that's why you can only do that right now for these planets with stronger signals. So that's the bigger planets with bigger atmospheres.
Wonder how many decades it'll be before we're looking for planets and seeing how much their CO2 is increasing.
Yeah, we're trying to do that. Yeah.
How far away and how long ago are these exoplanets that you're imaging?
How far? So we're not imaging any of them because it's only one pixel.
So the absence of them, the joint light.
How far away? It depends. I honestly don't really know, because for me it doesn't matter. It's like light years. Like the closest planet is 1 light year, which is Proxima Centauri b. But yeah, most of them are. TRAPPIST-1 is fairly close. I couldn't tell you off the top of my head.
But
exactly
we're talking about a number of light years rather than gazillions of light years.
Yeah.
Okay.
I googled TRAPPIST and it's 40.
40 light years of TRAPPIST. Thank you, member of the audience. Very good. Excellent. Could rocks provide a positive sign of former life on exoplanets or life on exoplanets? For instance, if there'd been an ocean and the atmosphere was lost, leaving a sedimentary rock like we find in former shallow seas on Earth. I imagine you can't yet detect that.
Yeah, that's really interesting, actually. I think a planet without an atmosphere, it would be hard to imagine life on the surface. I'm not a biologist, so I don't really know. Maybe they could have life underground. But usually we operate with the idea that if we're looking for a planet with life, the priority is to look for planets with atmospheres.
Yeah. Good. Okay. I don't know why one person is saying, oh, they're really stupid questions. There aren't, because we have a rule. There's no such thing as a stupid question here. So the spectra on the last slide, he was asking, is that from a star or from a planet around a star or from Earth?
This here? Yeah, so this is measuring this is the eclipse. So this is looking at the they extracted the thermal emission from the planet when it was behind the star.
So this is one of the TRAPPIST ones?
This is not TRAPPIST, this is LHS 3844b, so it's around the star LHS 3844. And
so the first bit is the name of the sun, and then the B is for the
exactly,
planet. Okay.
yeah. So this is like a rocky planet that's a bit bigger than Earth. Yeah.
Slightly mind-bending. So, do you know, I was going to ask you, I'll get this slide actually, get a bit out of the way. Do you know anything about what the geologists have decided it would be like, or the climate scientists have decided what it would be like, if you were on a planet that kept its face always the same way to the star? Would it be very much kind of big changes between the zones? Would you expect that there was any chance of an atmosphere or not?
It's hard to say if the chances of an atmosphere. I don't think we know that. There's a lot of, it also depends on if you're covered by ocean or if you have no ocean. We think, actually my office mate works on this where he does models of the mantle dynamics, and he's finding that you end up getting like all these volcanoes on the day side where like the mantle is kind of melting just only on the day side, and then making even like a continents and stuff on the day side, and on the night side nothing's really going on.
I mean,
Yeah.
isn't
Bit like a lava rock.
Isn't Mercury an example?
Is Mercury an example of that or not?
I mean, Mercury flying around the sun now.
Is
that not an example of what you're talking about?
I don't think.
No.
Yeah.
I don't think it keeps it the same side.
No, it's
You
not.
know, it's just a given.
Yeah.
I don't think it keeps the same side. Yeah.
I thought it did, actually, but then.
I might be wrong. I don't think it does.
No, I don't think it
spinning,
keeps
isn't
one
it?
side all the time.
Mercury's
Yeah.
spinning.
They're all spinning, it's just like whether it's
Yeah,
locked,
yeah,
whether it's
yeah,
synchronous to
yeah,
your
I
star,
thought
to its
about
orbit.
that, yeah.
I think Mercury's 2/3 tidally locked.
Sorry?
I think it's 2/3 tidally locked. So it goes round
A bit.
3 times every time it goes round twice.
So you can be permanently in the cold, can't
You can be in the cold for a long time, yeah.
you? Yeah, you never come out to the sun.
Yeah.
You won't in the cold sun.
I think there's like ice in Mercury's poles even, like people have found weird, like, that wouldn't be stable in high temperatures. Yeah, there's like lots of permanent shadows.
Sorry, I'm just trying to remember what I was asking. Yeah, can I ask, this business of, you said that you know there are volcanoes. Is that again a matter of modelling and guesswork, assumptions?
Yeah. That's
okay.
theoretical. I don't think there's a way of directly detecting a volcano on a planet. This comes
Unless
from...
you can visit it.
Yes, yeah, unless you can visit it. Yeah, but there's examples of volcanoes all over the solar system, so it's hard to imagine that they wouldn't be an outcome of geology.
And I guess the same thing, do you have any sense from, does it change if something's a water planet or mostly covered in water? Would that change what you're seeing or not?
I think you wouldn't have an ocean without an atmosphere.
Right.
I don't think it would be stable, I think it would just evaporate.
Yeah.
But
I mean, so I said water, liquid planet.
Yeah.
You might get something where it's very, very hot, but still lots of liquid underneath, but it could be anything. I mean, it wouldn't necessarily have to be water.
Yeah.
Yeah. So it's like an awful lot of what ifs.
Yeah.
Rather good, rather fun. Okay. Okay. How come, so this is about this spectrum.
Yes.
How come there are the 4 spectra for one planet? Is that because you're actually saying how much is made of each rock?
No. So yeah, these, I mean, I'm not sure if you can see very well, these are models. There's one
models,
data point that's right here.
Yeah.
So that kind of fits this basaltic model. That's really cool. These ones are just, we make these plots to say we compare the data point to different models and say which one fits the best. So yeah, I mean, that doesn't say it's definitely basalt. You could probably put lots of different lines here that fit that one data. Ideally, we go back to look at this planet and get more points, and then you can have a better idea of which model is the best. Also put more models on, but there's only 4.
So there might be something possible one day looking at whether you get a different spectrum when these things are liquid or solid, and then you might start to get more information about what the surface of the planet was like.
Yeah, I think for looking at like lava planets is hard because they just don't have a lot of these bumps.
Yeah.
So I think it's more flat. It's hard to say, but yeah. But we would know if a planet's lava just because if it's like 3,000 degrees, it has to be.
Yeah. Still making assumptions, but pretty reasonable.
Yeah.
Fair enough. Good. Yeah.
If you're using Stefan's law and the t to the fourth, you need a lot of points in your spectrum to know what temperature you've got. How do you get that many points if you've only got a few photons?
I don't know how many photons you need to get the right signal to noise, but the points I showed are actually bins. They have a lot more, and then they have to average them to see, because it's the photons itself will have their own noise. So the people that actually use the telescopes to collect the photons are just not me. I figured out, like, I need this much to be able to say that my signal is real.
Okay.
Yeah.
Okay. It's very thorough. I think we've run out of questions, but so I'm going to bring it to a close. I do know there's probably quite a high chance people want to chat to Claire while I'm clearing up, so please feel free before I take it.
Yeah.
Thank you so much for tonight. Yeah, in a minute. My thanks as usual to the Department of Pharmacology who give us this space to be in. It is getting lighter every time, the lights keep reflecting more and they turn more of them on. I will try and cure that at the moment. I haven't got through to whoever knows how to do it, so we'll see. Obviously thank you everybody for coming, thank you everyone for coming online, absolutely fantastic. The next 2 dates are both, of course, the same day because it's not a leap year, so 11th of February, 11th of March. Keep an eye on the website and the mailing list. If you haven't signed up, then Google Oxford Café Scientifique, and the front page has instructions about how to sign up on the website. I hope you're enjoying the videos of previous talks which I put up, so there's a big load of them which I uploaded over Christmas and the New Year. That went out on the mailing list. If you haven't got those because you weren't on the mailing list, you're really welcome to join it so you get future alerts. I'm going to carry on putting those links in to the emails for the next few times I email out as well. But also you can email me directly and just to ask, and that's absolutely fine. I can answer. Hope to see you again here next month. No, I don't have the topic sorted because people are messing me around, but we'll see. I've got several irons in the fire. I will be a lot more sorted next time. I feel like I'm back in harness now, so I'm like, okay, mental list of everything I need to do. So apologies for any of the little audio problems and things earlier. I will add Claire's beautiful video of the exoplanets on to the end of this video, so I'll record that separately and then tack it on the end so people can watch it again.
I would like to say that you're doing a tremendous job.
Thank you. It's a little bit more difficult, thank you. I think the person who really needs a clap today, however, is Claire, bringing her out on a January night. Thank you so much. I think we're all rather excited about this topic, as you can tell. It's probably been the best discussion we've had for a while. So thank you very much. Wait.